Hello everyone, we're here to do a couple of quick problems for Physics 202 at Texas A&M. Okay, one, and I'm making this up, I'm not giving any handouts on this. We have a wire carrying a current this way of 3 amps. We have a wire carrying a current this way of 6 amps. I want to determine where B would equal 0. I want to know where the magnetic field would be 0 with these two wires. Okay? Now, this isn't that hard to do, but it requires some thought. You have to know your right-hand rules. If you don't get right-hand rule 2 correctly on this, you're not going to be able to get it figured out right. Because you can't just assume it's anywhere. So I get my right-hand rule number 2. Remember, your thumb's the direction of the current, your fingers are the direction of the magnetic field. And I put my thumb in the direction of the current, and my fingers wrap around the direction of B. So B's coming out at the top, which would be dots, and going in at the bottom. So B top is doing this. A bottom one is going this way, so I put my thumb in the direction of the current, my fingers wrap around the wire at the direction of B, so B's going in here and out down here. Now, the two magnetic fields are going the same way between the two wires. That means the magnetic field cannot be 0 between the wires. So it has to be on either side of the wire, at the top or the bottom. Now, if the currents are going the same direction, the magnetic field would be 0 between the wires. But they're not going the same direction, so it cannot be 0 between them. Okay? So, how do I know where the magnetic field would be 0? Would it be up at the top or down at the bottom? Well, if you remember when we did electric field problems, the answer to that was that the magnetic field was 0, electric field was 0 on the side of the point charge that was smallest. In other words, if I had a positive charge and had a negative charge, and this is, say, 3 microcoulombs, and this is 8 microcoulombs, the electric field would have been 0 over here somewhere. And the reason for that is this charge is just overwhelming everything in its vicinity around it. This is like a baby screaming its head off. You don't hear anything but screaming baby. Over here you have a 3-year-old screaming her head off. Well, the baby's always going to be louder than the 3-year-old. One day, if you don't have kids, you will understand that when you do have kids. The baby's always louder than the 3-year-old. And when you're around the baby, you can't hear the 3-year-old. But you get over here, there's going to be a point where you hear him equally well. And the same thing works here. The magnetic field can't be 0 on this side of this current because the magnetic field will be too large, and all you're ever going to see is a magnetic field from this one. So it has to be 0 up here on the top somewhere. And that's important because if you're going to try to solve this, you have to have the distances correctly. Okay? Now, I never give the distance between the wires, so we're going to make that 0.2 meters. Okay? And we're going to call the distance up here where the electric field is 0 is x. All right. Now, for the equation for the magnetic field, it's mu naught I over 2 pi r. So what we're going to say is B top equals B bottom. Okay? So mu naught I top over 2 pi r top equals mu naught I bottom over 2 pi r bottom. Now there's some canceling that can happen here. The mu naughts can cancel, the 2 pi's can cancel. So this just turns into I top over r top equals I bottom over r bottom. Now the math here isn't very hard, and working on this from here isn't very hard either, because we have the two currents. The top current's 3. The radius from the top wire to our point of 0 is x. Our current on the bottom is 6, and the radius from the bottom to our 0 point is x plus 0.2. Now, from here, you're just going to cross multiply and solve, so we're going to get 6x equals 3 times x plus 0.2. 6x equals 3x plus 0.6. 3x equals 0.6. This should get x equals 0.2, but I've had a long day and a stressful week, so I'm grabbing a calculator to verify because, you know, we don't want to screw anything up. Some of you are going to be watching this video in the morning and go, oh, I need to watch that. And I screw up the math. That's not good. So it's 0.2 meters above the top wire. Okay. Now, alternate way to ask this question is not determine where b equals 0, would be determine where we may place a third wire so the force on that wire equals 0. Now that's the exact same problem, because the magnetic field is 0, the force on that wire would be 0. Okay, so that's the exact same problem, and we don't have any worries about that. All right, so there you go. There's this problem. I'm going to put these two as the same video because the video isn't going to be very long. But here's another problem to discuss. I have the Earth. We have a North Pole up here and a South Pole down here. The magnetic field around the Earth leaves their North Pole. Okay, it leaves the North Pole. It goes into the South Pole. And of course, it's going to run parallel around the edges in order for that to work. Cosmic rays travel perpendicular to the Earth's surface. So my handwriting's a little sucky right now. It's been a long, crazy week. And I mean a long, long, crazy week. Okay? So cosmic rays are always coming in like this. Always perpendicular. That green pen, I do not like it. Let me find a different green pen real quick. There we go. They always come in perpendicular to the Earth's surface. So they're always doing this. Okay? So the question here is where will the concentration of cosmic rays be the largest? Where will the concentration of cosmic rays be the largest? Okay? All right, now remember the magnetic field deflects charged particles. And cosmic rays are always positively charged because they're basically hydrogen atoms with electrons stripped off. Hydrogen or helium, but mostly hydrogen. And so they're positive. And you look at this, let's say we're at the North Pole. We have our magnetic field going this way. We have the velocity of the cosmic ray going this way, and this is the North Pole. The B field and the velocity are parallel. And when we're parallel like this, that means there's no force. We go to the South Pole, the magnetic field's going the same way, but the velocity's going this way. This is the South Pole. We have the same thing, no force. That means at the North and South Poles, these cosmic rays are not deflected. They just keep going the same direction they ordinarily would have went. Nothing changes them. But if we look at the equator, we have our magnetic field going, let me look back at my picture so I draw it correctly, going downwards. I'm drawing it, I knew I was drawing it wrong. According to my Earth picture, my magnetic field is going this way, but my cosmic rays are going this way. That's my velocity. And if you get a right-hand rule number 1 out, your magnetic field's going down, your velocity that way, that means the force is coming up out of the page. And with the force coming up out of the page, they're deflected. So they're deflected at the equator because of right-hand rule number 1. Remember, boogers, this point's of boogers. This is your velocity, this is your force. So we have our boogers down, our velocity that way, so my force would be coming straight up. Kind of hard to twist my hand around that way. So the answer to this question is the cosmic rays would be, the concentration would be largest at the North and South Pole. Okay? And there you go. There's a couple of quick questions for Physics 202. I hope you find them helpful. For those that are not in Physics 202 and you found them, I hope you find them helpful. And I will talk to you all later. Have a good night.